wabarakatuh. Today I would like to introduce about our assignment, which has been distributed by our lecturer, who is Miss Anis. Today our group will be presenting about buck converter. Our group are solely or compact with three members, which is Muhammad Firdaus Razak, HAZIQ, and SHAUQI. Okay. For the introduction, we have a simple one, which is a buck converter that is used to reduce a level of DC input voltage. Okay, that's for the introduction, and I will pass to the next person.
Hello everyone, my name is Muhammad Mashaki Mamazaki. I want to present the circuit operation. The MOSFET is a switch and this is a voltage source, diode, capacitor, resistor and load. When the MOSFET is turned on, the voltage source creates a loop by the supplying current to the inductor L1. As a result, diode D1 inhibited by the positive voltage in the cathode in the opposite loop. The current is route to the resistor and the capacitor. The phase result in the collapse of the magnetic field of the inductor. The inductor voltage becomes more polarized as a result. When the MOSFET is turned off, the storage current is changed of the inductor and the capacitance source current to flow from inductor L through diode D1. Capacitance C and load current R, load resistor R. Capacitance C all experience current flow simulation, forming another loop. Until the switch is turned back on, no current flow between the input source and the switch.
Of our simulation, which is the output voltage, the average conductor current, maximum and the minimum inductor current, which has max and the minimum of our current. Okay. This will be the comparison for part A. This is the formula that you can see that the output voltage will be 0.1 and the average in the current is 0.12 percentage. This is for the percentage and this is for the total of the current. Okay, that's okay. Now pass to the next person. Thank you.
Okay, next I will tell you about our simulation result. Okay, this is the circuit that we use to get the simulation result. We also add a PWM in the circuit to control the time amplitude of the output current and voltage, in addition to reducing the harmonic distortion. After we simulate this circuit, as you can see, the output voltage is 1.305 volt and output current is 3.659 ampere. For the average value for voltage is 1.316 voltage and average value for current is 4.385 ampere. Okay, next. Okay, this is the waveform that we get after the simulation. For the first wave is the PWM waveform. The second is the current measurement waveform, and the third wave is voltage measurement waveform. Okay, when we zoom the optical waveform in between 0.6 ms to 0.62 millisecond, we can see more clearly the output waveform values for voltage and current. The minimum voltage produced by the circuit is 1.19 volt, while the maximum voltage produced is 1.213 volt. For current, the minimum value produced is 3.3 ampere, while the maximum current is 4.8 ampere. Okay, now you can see the comparison between our simulation and our calculation. They are no much different. This show that our calculation is correct. Okay, that's all for me. Thank you.
So next we have the component choosing. So there are 4 types of component choosing that will be choose inside the buck converter. So first of all we have Schottky diode. Next for the inductor and capacitor, and also finally we have the MOSFET. So for diode we will be using Schottky diode. Schottky diode is used due to their quick recovery time, and Schottky diode also are suitable for discharging buck converter. Next we have the voltage setting. The greatest voltage setting across the diode is known as VPRM or PIV, and we have the peak inverse voltage VPRM for an ideal switch is equal to the maximum input voltage VDC max, and finally we have the VPRM is equal to the VDC max plus the maximum forward voltage drop VCW across the switch in a non-ideal condition. For the current rating, the average forward diode current is determined from the diode current waveform. T off is taken into consideration in the computation since the diode conduct when the switch is off. So we have the inductor. For the characteristic, we must have maximum input voltage, minimum input voltage, maximum output current, frequency of operation, output voltage, and the minimum V output current. The inductor design must have the ability to withstand the desired ripple current, and the duty cycle you intend to apply for your PWM signal will determine the right value for the inductor. Due to the inductor constant switching at the same rate as the PWM signal, ripple will be added to the current being transmitted to the output. So we have the capacitor. The capacitor is close to the converter, and input capacitor act as a source for the high frequency current, eliminating the need for a separate DC supply. Depending on the converter operating mode, the input current can have a peak value that is several times higher than the average. Therefore, the capacitor provides the peaks, or more precisely the AC component, and the DC supply gives the average component. During the converter off period, the DC supply charges the capacitor, the switching frequency current loop is brief, and radiation from connection is reduced when the capacitor is kept closed. The capacitor plays a critical role in providing stable current to the load as the PWM switches, and the capacitor also allows input peak-to-peak ripple voltage and allow input transient undershoot or overshoot. The capacitor voltage setting should meet reliability and safety requirement. For this example, all input capacitors are rated at 25 or above. The following discussion focus on meeting electrical requirement, optimizing performance, and lowering size and cost. Finally, we have MOSFET. So the majority of transistors used today, including flash memory, processor, random access memory, application specific integrate circuits, and more and more metal oxide semiconductor field effect transistor or known as MOSFET. MOSFET can be thought as a voltage control current limiting device. In a buck converter, the output voltage is always higher than the input voltage, whereas in a buck converter, the opposite is true. Circuit for switching also use MOSFET. MOSFET does not require constant supply of driving current to maintain the on state. In contrast to bipolar junction, tungsten BJT, the rival form of power transistor. MOSFET can also provide faster switching time, less switching power loss, lower on resistance, lower risk on thermal runaway. MOSFET also are frequently employed in switch mode power supply, SMPS, and switching element for a power factor protection. So, and finally, for ending our presentation, the conclusion of our project assignment, the key details of this converter are all presented in full, which satisfies the assignment goal of explaining the buck converter. Additionally, the result of simulation and computation are essentially the same. It is possible to do true and precise analysis using information from the lecture notes and the internet. That's all for me. Thank you.